In this video, we will continue our discussion on molecular mass, but we will learn how to calculate molecular masses for molecules or formula mass, so formula unit or ionic compounds. When we calculated the molar mass of a particular element, all we had to do was to look at the periodic table and look underneath the symbol for that element, and whatever that number is, that's how much 1 mole of that particular element weighs in grams. But we don't just deal with individual elements in chemistry. We know that elements combine together to form molecules. So how do we figure out the molar mass of molecules? It is one extra step. We first have to figure out what types of elements make up that molecule and how many of each do I have. The mass of one molecule is made up of the masses of all the atoms that it contains, of all elements. Similarly, the formula mass for an ionic compound is the sum of the atomic masses of the formula unit. Let's take a look here. We have to figure out the molecular mass of H2O. Well, I can see that I have two types of elements here. I have hydrogen and oxygen that make up the mass of water. I have two, so this little subscript here by hydrogen tells me that I have two hydrogens, and it's not written here, but it would be a 1, and I only have one oxygen. Since I have two or twice as much hydrogen as I do oxygen, I have to take that into account. So I have each one of these. If I go to the periodic table and I look under hydrogen, I would find 1.008 AMUs. So if I want to find the mass of two of those, I would have to multiply by 2. So 2 hydrogen atoms would weigh 2 times 1.008 AMU. If one of them weighs 1.008, 2 of them would weigh twice as much. And I have only one atom of oxygen, which, if I look under the oxygen, weighs 16.00 AMUs, because I'm talking about individual atoms right now. And that is how much one oxygen atom weighs. So to figure out how much the molar mass of one water molecule is the molecular mass, right? That is going to be the sum of the individual components. So 2 hydrogen atoms, the mass of those two, plus the mass of one oxygen atom. And if I do this math, so do the multiplication first, then the addition, you would get something similar to this, 18.02.016 AMUs. That is for one molecule of water. Let's look at a formula mass for an ionic compound, which is sodium chloride. If I look under sodium, one sodium atom weighs 22.99 AMUs. One chlorine atom weighs 35.45 AMUs. So if I add these together, I would get 58.44 AMU, and that is the mass of one NaCl molecule. I mean, this is an ionic compound, so that's the formula mass for that. Now, how do I calculate the molar mass for 1 mole of water or sodium chloride? We do the same thing, but instead of now looking at AMUs for individual atoms, we look to moles. The numbers are the same. So if I'm looking at hydrogen, right? So water is made up of 2 moles of hydrogen and 1 mole of oxygen, make 1 mole of water. Each mole of hydrogen weighs 1.008 grams. Since I have 2 moles of hydrogen, I would have to multiply that by 2 to figure out how many grams 2 moles of hydrogen weigh. And then I have 1 mole of oxygen that weighs 16.00 grams. The sum of those two gives me 18.016 grams. Remember that the grams is the macroscopic quantity, and the macroscopic quantity is the mole, not the atom and AMUs. So gram and mole are macroscopic. The same idea for an ionic compound. Sodium chloride is NaCl. So I have 1 mole of sodium weighs 22.99 grams, because that is the number underneath the element in the periodic table. And then I add to that the 1 mole of chlorine, which weighs 35.45 grams. If I add those two together, I get 58.44 grams, which is what 1 mole of NaCl weighs. This is how we calculate molar masses. We figure out how many of each element we have. If we have a subscript of 1, it's not written, but every other subscript will tell us how many. So 2 moles, 3 moles, 5 moles, etc. And that is what we're going to multiply the mass by. So in this case, for hydrogen, it was 1.008, which is the mass of 1 mole. But I have 2 moles, so I have to multiply by 2. If I have 5 moles, I have to multiply by 5, etc., etc. Let's look at a sample problem. I'm going to do A for you and then give you a chance to do B through D. Here's my molecule. I have N2O5. These little subscripts tell me that I have 2 nitrogens and 5 oxygens. Note that if I have parentheses here, typically this happens with polyatomic ions. So as you can see, I have 3 oxygens in this polyatomic ion in parentheses, but then I have 2 of those. When you figure out how many oxygen atoms do you have, you multiply the subscripts. You don't add them. That's a very common mistake. Students will just do 3 plus 2. I have 5 oxygens. Actually, it needs to be 3 times 2, 6 oxygen atoms, or 6 moles of oxygen atoms. So here is how I would calculate the molar mass of N2O5. I have 2 moles of nitrogen. If you look under nitrogen in the periodic table, you will see that 1 mole weighs 14.01. Because I have 2, I have to multiply that number by 2, and I get 28.02 grams. 5 moles, I have 5 moles of oxygen, right? 1 mole of oxygen weighs 16 grams, as we saw in the previous slide, but I have 5 of them, so 5 times 16 gives me 80 grams. You always have to multiply it by the subscripts next to each element, because that's how many moles you have of each. And then the last step is adding these two together, giving you 108.02 grams. And that is how much, oops, I'm missing a 5 here. 1 mole of N2O5 weighs. I am then going to give you, I'm going to fix that, by the way. I am going to give you a little bit of time to work B through D. Follow the same pattern, and remember that when you have a polyatomic ion in parentheses and then another subscript outside the parentheses, you multiply the subscripts together to figure out the oxygen. For chlorine, because it's 1, you would just do 2 times 1, 2 equals 2. All right, try them and see how you get on. Here is our little trusty conversion flow chart. Once again, we've got grams, 2 moles, and particles, atoms, molecules, or ions, or formula units. Note that nothing here has changed. This is very similar. We're just adding molecules, ions, and formula units. The first flow chart in the previous video only had atoms, but the particles, including molecules, ions, and formula units now, so we're expanding a little bit, they work the same way because I will have moles of whatever, moles of water, moles of sodium chloride, and to figure out how many individual molecules I have, I will still use Avogadro's number. So this part doesn't change, it's just the unit. Instead of moles of atoms, now I can have moles of molecules or moles of ionic compounds or moles of ions, etc. But the flow chart really remains the same and the calculations remain the same. The only difference here for molecules or ions or formula units is that we have to figure out the correct molar mass by adding all the components together, the masses of all the components. Now we can combine multiple conversion steps in one single calculation to make our life a little easier. You don't have to do this if you're not comfortable with it. Please don't. I'd rather you get the correct answer than figure out how to do it in one step. So if you're more comfortable breaking it up, that's fine. But just make sure that you know how this actually flows. So you can take the answer from the first step and bring it down to the second step, and that's your starting point for the second step, etc., etc. So if I'm trying to figure out how many hydrogen atoms there are in 500 grams of H2O, there isn't an immediate or an easy way to go from grams to atoms, right? I still have to go through the flow chart. But now I have kind of one extra step because I have to account for how many hydrogen atoms I have in one molecule of water. So here's how I would go about it. I once again start with the amount I'm given in the problem, which is 500 grams. Using the molar mass of water that we calculated already, if you want to, you can go ahead and recalculate it to make sure that you get some extra practice, but it's 18.016 grams for every mole. Follow the little flow chart. All I'm doing here is I'm taking the grams of water and I'm converting them to moles of water. So this is my first step. My grams will cancel, leaving me with moles. Now I could stop here and do this equal to, and then do the division. 500 divided by 18 point something will give me a number, and that would be moles of hydrogen. So that would be my first step, and I could break this up and not have it all in one long step. But then know that you will take that number, moles of water, and that will be your starting point in the second step. It's not going to be this conversion factor. Once again, you don't start with conversion factors. You would start with the answer you get from the first step, bring it down to the second step, and then use the second conversion factor. In this one, we've just done it all in one calculation. So now that I have moles of water, I can figure out how many molecules of water I have by using Avogadro's number, because I know that every mole of water contains 6.022 times 10 to the 23rd water molecules. My moles will cancel, leaving me with water molecules. But the question is asking me how many atoms of hydrogen I have for each in 500 grams. So if I just stop there, that's only water molecules in 500 grams, not hydrogen atoms. The last step is to relate or to convert to hydrogen atoms. And I know by just looking at the molecule of water that for every one molecule of water, I have 2 hydrogen atoms. I have only 1 oxygen atom, but I have 2 hydrogen atoms. And here's my last conversion factor. 2 hydrogen atoms for every 1 water molecule. Water molecules will cancel out, leaving me then with only hydrogen atoms. And then what I would have to do is take 500, multiply it by 6.022 times 10 to the 23rd multiplied by 2 divided by 18.016. So multiply the top numbers divided by the bottom numbers multiplied together. And it will give you 3.343 times 10 to the 25th hydrogen atoms. Note that this is more than I would have water molecules because I have twice as many hydrogen atoms as I do water molecules. Here's a sample problem. Determine the number of moles of CO2 in a 10 gram sample of CO2. Looking at my flow chart, I'm starting with a mass and I want to determine moles. What do I need to do? I need to figure out the molar mass of CO2 first before I can convert to moles. Here's how I'd go about it. I have 1 mole of carbon plus 2 moles of oxygen. 1 mole of carbon weighs 12.01 grams if you look in the periodic table. And then I'm adding to that 2 times each mole of oxygen weighs 16 grams. So 2 times 16. 12.01 plus 32 gives me 44.01 grams. And that's the molar mass. So 1 mole of CO2 weighs 44.01 grams of CO2. However, I still need to figure out the number of moles in 10 grams. Note that if 1 mole weighs 44.1 gram and I have a sample of 10 grams, I will have fewer than 1 mole because I have less than 44.01 grams. Start with the amount you are given in the problem, and here's how I would go about it. I would write 10 grams of CO2 multiplied by 1 mole of CO2 weighs 44.01 grams of CO2. I write my molar mass as a fraction where my grams are at the bottom and the moles are at the top because I'm converting to moles and I want to get rid of my grams. If it were the opposite, so if I started with moles and wanted to end up with grams, then these two numbers would be inverse. I would have the grams on top and moles at the bottom. Also note that the 1 mole always goes together and the number goes with the grams. These grams will cancel, so all I have to do is take 10 divided by 44.01 and it's 0.2272 moles of CO2. Note that I need to have 4 significant digits for my answer because my measurement here has 4 significant digits. These trailing zeros are significant because there's that decimal point right there. I will give you some time to try to figure out the mass of 0.905 moles of sodium chloride. You first figure out the molar mass of sodium chloride. So how many grams does 1 mole of sodium chloride weigh? You can repeat that or you can look to the previous slides because we did that earlier. And then in this case, use the flow chart to start. You're starting from moles and you want to calculate the mass in grams. So you're doing the opposite of what we did here. Start with this number and use the mass of sodium chloride, the molar mass, to figure out how many grams 0.905 moles weigh. Let's take a look at another sample problem. We have to determine the number of water molecules and the numbers of hydrogen and oxygen atoms in 3.26 grams of water. Okay, what is the first thing we need to do? The first thing we need to do in any of these problems is figure out the molar mass of my water. The molar mass of water, I have 2 moles, right? This is my water. I have 2 moles of hydrogen and 1 mole of oxygen. 2 times 1.008 grams, that is the number that's underneath hydrogen in the periodic table, plus 16 grams of oxygen. Note I don't multiply this number by anything because I only have 1 mole of oxygen. This is the number that's found underneath oxygen in the periodic table. If you do these calculations, you get approximately 18.02 grams of H2O. Then I start with the amount that the problem gives me, which is 3.26 grams. 3.26 grams. Using your flow chart, convert to moles first. You cannot find individual molecules from grams. You have to convert to moles by using the molar mass that we just calculated. So 3.26 grams multiplied by my conversion factor. 1 mole of water weighs 18.02 grams. My grams will cancel, leaving me with moles. And then to convert to water molecules, I know that 1 mole of water contains 6.022 times 10 to the 23rd water molecules. My moles will cancel, leaving me with water molecules. Once again, follow the chart, the flow chart that is provided for you. That should be very helpful. And then I would do 3.26 times Avogadro's number divided by 18.02 to get 1.09 times 10 to the 23rd. Note that these do not count for significant digits because they're exact numbers, but 3.26 does, and that's why I have 3 significant digits. I am not done, however, because I need to figure out how many atoms of hydrogen and oxygen I have. But now that I know how many water molecules are contained in 3.26 grams, all I have to do is relate that back to hydrogen and oxygen atoms. I know that 1 molecule contains 2 hydrogen atoms and 1 oxygen atom. So here's the answer that we got in the previous slide. This is how many water molecules we have. And we have 2 hydrogen atoms for every molecule. My molecules will cancel, leaving me with hydrogen atoms. So 2.18 times 10 to the 23rd. For oxygen atoms, it's going to be the same because I have 1 oxygen atom for every 1 molecule of water. And I'm multiplying the number of water molecules by 1 oxygen atom per 1 molecule, and I get 1.09 times 10 to the 23 oxygen atoms. I will give you a little bit of time then to work on this part B here. We have to determine the mass of 7.92 times 10 to the 19th CO2 molecules. You are starting with molecules. You know that 1 mole of CO2 contains 6.022 times 10 to the 23rd CO2 molecules. So use Avogadro's number to convert to moles. Then once you have moles, convert to mass using the molar mass of CO2. How do you calculate the molar mass of CO2? You have 1 carbon, so 1 mole of carbon and 2 moles of oxygen. 1 mole of carbon weighs 12.01. 2 moles of oxygen weigh 2 times 16, 32 grams. Add them together, find the CO2 molar mass, and use that to convert from moles to grams. Okay, and here's another sample problem. We need to determine the number of magnesium and cyanide ions present in 73.8 grams of magnesium cyanide. You first need to figure out the molar mass of magnesium cyanide. You have the magnesium plus 2 carbons plus 2 nitrogens. Once you have that, follow the flow chart. You're starting with mass in grams, convert to moles. Then once you have moles, use Avogadro's number to calculate how many molecules or formula units you have for, this is an ionic compound, of magnesium cyanide. Then once you have how many molecules of magnesium cyanide you have, remember that there is one magnesium ion for every magnesium cyanide molecule and two cyanide ions for every molecule of magnesium cyanide. Follow the example with the hydrogen and oxygen atoms found in water molecules. It's very similar, just the numbers will be slightly different because these are different elements.